We are going to measure position using percentiles. We're going to interpret relative frequency graphs and cumulative relative frequency graphs. Measure position using z-scores. We'll transform data, and we will also define and describe density curves in brief. So, first things first, you guys have heard about percentiles before. If you take your little brothers or sisters or nieces or nephews to the doctor, they measure their height and their weight, and they say, hey, your kid is like in the 13th percentile. Well, what's a percentile? It's the value with p% of observations less than it. The key part is less than it. So if I say Jenny earned a score of 86 on her test, how did she perform relative to the rest of the class? Here's her score at 86. How many people are below her? So we count, I'm like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. There are 21 out of 25 students in her class that were below her. 21 out of 25 students are below her. Divide it, you get 0.8. 0.84, I'm sorry. She's at the 84th percentile, so we say this. 84% of students in Jenny's class scored below, you can say scored below her or scored below an 86. Percentile, how many lie below wherever you're at? You try the next 3 at the bottom. If you're at 65, there's 2 65s. It's still counting how many are below that 65. So here there's 3 that are below 65. 3 out of the 30 gives you 0.1 or 10%. With the percentile, from what I understand, we always round. I always see them rounded. I guess I haven't really looked into it, but always round it. A cumulative relative frequency graph. We kind of have 2 and 1 here. This is cumulative because it keeps adding on. We can find our relative frequency first, though. This is the age of the first 44 presidents and when they were inaugurated. So between that range of 40 to 44, there were 2 presidents that were inaugurated at that age. So my relative frequency is 2 out of 44. We divide that and we get 4.5%. In this age range, 45 to 49, I have 7 out of the 44 presidents, and in that range, that was 15.9% of our presidents, and so on. Here we have 13 out of 44. It's 29.5%. What is 12 out of 44? This is 27? That makes more sense. Sorry. And then we have the cumulative frequency. And when we talk relative deals with percentages. So the cumulative frequency, in this first range, I'm just at 2. I only have 2 presidents between 40 and 44. Cumulative means we keep adding on. So now in this next set, I have 45, age range 45 to 49, there's 7 more. So 2 plus my 7 gives me 9. And for this next set, I'm adding these all together, so I have 9 plus 13 more gives me 22. Or if you want to add all these numbers together, 2 plus 7 plus 13 plus 12, that's going to give us 34. Add them up, 41, and then 3 more gives us 44 total. So that's your cumulative frequency. Relative frequency, divide it out. We have 2 out of 44, we have 9 out of 44, 22 out of 44, 34 out of 44, 41 out of 44, 44 out of 44. And then you can find your percents. And then when you finish that, check out how that plays into the graph. Do you see how that graph works? So between 40 and 44 years old, we're at like 4.5%. And if we keep building on this, now between 45 and 49%, we are now up to about 20.5%. And then with the next age category, we are now up to 50%. And it just builds to get you till you get to 100%. What does this give you? This would give you your percentile. So if I say, was Barack Obama, who was inaugurated at age 47, unusually young? Age 47 is roughly in here. So I can use this now to find my percentile based on all the presidents that we have information from. So here's age 47. We carry it over. That is approximately like the 11th percentile. You see how that works? So was he unusually young? Let me try and talk you through this. We could say, yes, he was young. Why? Only 11% of presidents were inaugurated before age 47. So if we have all this information of all the presidents, where do these presidents lie based on their age? So now this is kind of the flip side of it. Estimate and interpret the 65th percentile of the distribution. Here's my percentages. If this is 70 in the middle, 65 is roughly in here. So we come across till you hit your line, drop it. I don't know, where are we at? 57? 58? So interpret it. How do we interpret a percentile? It's how much lies below it. We have 65% of presidents were inaugurated before 57 years old. Or before age 57. That would make more sense, before age 57. Or before they were. So that's one way for us to help find where individuals lie in a set of data. What's their position compared to everybody else? State median household incomes. Here's a table showing the distribution of median household incomes for 50 states and the District of Columbia. So what are we totaling it out of? 51. Be careful there. So this is out of 51. Go through, do the same thing we just did, and then see if you can figure out the pattern to fill in the blanks on the top of that next page. Like on this one, if we have the 0.50, comma, 0.49, that's telling us 49% of the states had household median incomes less than 50,000. So what's this next 0.55, comma, 0.07 or 0.725 tell us? 72.5 of the states had median household incomes less than 55,000. We have 23.5% of the states had median household incomes between 50 and 55,000. So from 50 to our 55 down here, that's a difference of $5,000. And so what's the difference between our percentages from 0.49 to 0.725? If we subtract, that's where that 23.5% comes from, or 0.235. If we have a household income at $50,000, 49% of the houses had income less than that. And if we have houses at $55,000, 72.5% had income less than that. So what's in between 72.5 and 49%? If I subtract those two, it's a difference of 23.5%. Use your graph, draw on your lines. At what percentile is California with a median household income of $57,445? Again, we're approximating as close as we can get. We draw a line up to the line and over, That's about roughly 0.8, turn it into a percentage, 80%. In this one, going back to chapter 1, first quartile, your quartiles are based on 25%, right? So if I say the first quartile, I'm looking for the first 25% or your 25th percentile. So here is roughly 25%, carry it over, drop your line, and interpret for me. About 25% of the states had median household incomes less than $45,000. It's always so much percent is less than this position. Remember when we did our box plots? We had Q1, your median, your Q3, and your max. It was divided into 4 parts. Quartile or core is like 4. So 100 divided by 4 is your... Other questions there? Measuring position with z-scores. Have you heard of z-scores before? Some of you, maybe not. Have you heard of a standardized score? Here's what happens. Sometimes, well, often, I give you a test and stats class, and we could figure out, well, what's your position compared to everybody else in the class? How did you do compared to everybody else in this class? When we go to Mr. Blodgett's class, Mr. Blodgett is going to have maybe 10 less students than me. I don't know. And in his class, we could figure out what's your percentile there so that we can compare the two. Well, sometimes what happens is we do something called standardized. We take our scores and we come up with what's called a z-score or standardized value so that it's a basis of how did you do compared to everybody else in your class without looking at percentages. A z-score is how many standard deviations from the mean an observation falls and in what direction. So they do not give you this until lesson 2.2, but I want to show you this because I think this kind of helps give you a little bit better visual of what's happening here. If you have, this is called our standard curve or standard normal curve. If you have the class average on your test, you're going to be right in the middle, and this is where we have what's called a z-score of 0. You are the average, you are not any deviation from the mean. Typically what happens is we have 1, we have 2, and we have 3 standard deviations above the mean. It goes a little bit beyond that, but not much. And then you have 1, 2, and 3 standard deviations below the mean. And there's a formula to help us figure out how many standard deviations are you above or below the mean. So when I say find your z-score or say find your standardized value, it tells us to take the x value minus the mean, and we divide by standard deviation. So here's this example. Jenny earned a score of 86 on her test. The class mean was 80, and the standard deviation is 6.07. What is her standardized score? So when we look at this, if she has an 86 and the class average was 80, she obviously scored above the mean. Well, how much better did she do than everybody else? What we need to do is we need to find her z-score, her standardized score. We take her score minus the class average, and we divide by the standard deviation. Do the math, you get 0.99. Excuse me. So how do we interpret this? We say Jenny scored 0.99 standard deviations above the mean or above the average class score. 0.99 standard deviations above the class average. So where's she at? She's somewhere roughly in here. She's above average, not the top, but better than most. So like I said, we can use Z-scores to compare position of individuals in different distributions. So again, we're still using Jenny earned an 86 on her stats test. Class average was 80, standard deviation was 6.07. She earned an 82 on her chem test. The chemistry scores had a fairly symmetric distribution with a mean of 76 and standard deviation of 4. On which test did Jenny perform better relative to the rest of her class? We just did this, and we had 0.99 was her Z-score for the stats, right? From that last example we just did. Oh, this is supposed to say chem. She scored an 82 on her chem exam. The class average was 76 with a standard deviation of 4. And do the math. We get 1.5. So she's 1.5 standard deviations above the class average in chemistry versus 0.99 in stats. Which one did she do better on? The chem exam. She had a higher Z-score for the chem exam. 82 minus 76 is 6 divided by 4. Yes. Be careful there. If you type this all in at once, you need to put parentheses around that because otherwise order of operations is going to goof you up. I'm glad you said that because I'm sure you're not the only one. On the next page, try wins of Major League Baseball and home run kings. Let's do this. For the sake of Z-scores, it would be good to go out 2 digits to go to the hundreds place to round it, and you'll see why later, but it'll be good practice to get in the habit right now of rounding to the hundreds place when you do these. So we look at these Z-scores, and we see which one is the highest. They were all phenomenal. To be 3 standard deviations above the mean is just basically unheard of. And we'll see why in the next section. But this is like saying 99% of the people are below you. So to be at 5 standard deviations above the mean, you're like never ever going to see that. That's just outrageous. So really, all the players' home runs were outstanding because they were 3 or more standard deviations above the mean. However, relatively speaking, because we look at these and we're comparing them all to the same scale, Ruth is the champ as seen by his home runs at 5.44 standard deviations above the mean. All right, this transforming data business, it really isn't as lengthy as it looks in your notes. Transforming data. So what happens when I curve your tests? I do this right here. I either add, I never subtract by a constant. What I do is to curve it is I add a point or 2 points to everybody's test score. We add we add our constant, that 1 point, that 2 points to the measures of center and location. But we do not change the shape of the distribution or the spread. So on your paper, circle these. Circle your mean, circle this set of numbers. Because if you notice, this is what it was before, and when I add or subtract by that constant, these are the ones that change. It's taking your data and it's just shifting it one direction or the other. Does how much it varies? Does your standard deviation change? No. Does your range change? No. All we're doing is just sliding that data. It's your average that'll change, the minimum will change, your Q1, your median, your Q3, your max, but all these ranges, that variation, that does not change. When we multiply or divide by a constant, these change nearly everything. The only thing it doesn't change is the shape. You'll notice from here to here, it's still skewed to the right. It is more spread out. The shape stays the same. So what changes though? All of these numbers are multiplied or divided except for n. What does n stand for? The number of individuals that we have, number of your pieces of data. So I look at this example. We've got test scores. Suppose the teacher was nice and added 5 points to each test score. How would this change shape, center, and spread? Compute the new scores and display the result in a dot plot below the one above. This is what we're going to do. When we add or subtract, we look back at that last example that I just gave you. Does it change how many individuals we have? No. Does it change the average? Yeah, it shifts the average up by 5. Does it change my standard deviation? When I add or subtract, it doesn't change how much the data deviates. My minimum value will increase. My Q1 will increase. Median increases. So does Q3. So does the max. But again, your IQR and your range, those are going to stay the same. So I was looking at the notes, the ones that we had circled. I'm like, the mean changes, and then these other 5 change. So with this one, I added 5, and with these, I added 5, but everything else stayed the same. I'm just using this example as a guide. IQR is not supposed to be in there, just like this. So what do you notice? Tell me about the shape. Does the shape change? No, if you take the data and you just slide it, the shape does not change. So you can make a note of that. How about the center? What happens to the center? It increases by 5. What happens to the spread? The spread stays the same. You could tell me about outliers, but what else changes? You could say the measures of position, bless you, increase by 5. Because these right here would be referred to as your measures of position. Your min, your Q1, median, Q3, your max. Those measures of position increase by 5. Look at the next one. When we multiply or divide, you can fill in those boxes which ones change. Suppose the teacher in the previous alternate example wanted to convert the original test scores to percents. Since the test was out of 50 points, he should multiply each score by 2 to make them out of 100. Here are graphs and summary statistics for the original scores and the doubled scores. So when we multiply by 2, is it going to change my count? No, but all the rest of these it's going to impact. So you can multiply all those by 2, get your new set of numbers. It's going to impact the mean. It's going to impact the standard deviation. It's going to impact your minimum. So what happens? The center, the spread, the location of all these values, center, spread, and location are all doubled, multiplied by 2. The shape is still the same, it's just more spread out. The shape stays the same. Except it is more spread out. It's still skewed, it's still got your same clusters and gaps. Last page. Give me like 2 minutes, tops, okay? Always plot your data and make a graph. We've talked about that before. Plot your data, make a graph. Look for an overall pattern. Tell me about your socks. And we calculate numerical summaries. That's nothing new. The new one today is number 4. Sometimes the overall pattern of a large number of observations is so regular, it's so symmetrical that we can describe it by a smooth curve. It's like this is distinctly what's happening. We can put a smooth curve over it. A density curve is a curve that 3 things. It is always on or above the horizontal axis. It's never going to be below the axis. It always has an area of exactly 1 underneath it. And what does it do? It describes the pattern of the distribution. So this always has an area of 1 under it. Suppose I take this extra piece that's sticking out of the top here. I could smush it and squeeze it and rework it, and these purple bars that are outside of the curve would fill in this white space that's not accounted for there. Okay? Talk to me here. If the data is symmetrical, you guys have seen this, median and mean are in the exact same location. If it's skewed, your mean is going to be slightly further into the tail. Two things to pay attention to. Your median is your equal areas point, and your mean is like the balancing point. So if you're to balance it, where would you balance it at? Here's where we would balance it. This median is like the equal areas point. Where's the area equal on both sides of it? Cool?